All right, we're going to do some more counting, this time some generalized permutations and combinations. And I think this idea is best introduced with an example. So consider the word Mississippi. And I want to figure out how many ways, how many distinct arrangements are there of the letters in the word Mississippi. So this is like a permutation problem, right? Like we're counting different arrangements of a given set, right? Just mixing up the orders. But not all the ways I could mix up the letters are distinct because we have some identical letters. Like if I just swapped these two S's, that wouldn't be a distinct arrangement, right? It would look exactly the same. So we have to take that into account. And let's see, if you count them up, there are 11 letters total. And if all letters were distinct, there would be 11 factorial arrangements. Of course, that's not the case. But what we can do now is just count how many distinct letters we have and how many of them. So there are, let's start. We've got one M. We have 1, 2, 3, 4 I's. We've got 4 S's. And we've got 2 P's. And that accounts for all 11 letters. There are 11 spots to fill with these letters. Right? I'm thinking of the word Mississippi as basically a list of spots, and I'm just going to put some letters in those 11 spots. And what we're going to do, what we're going to do is we're going to pick the spot that gets the M. I'm just going to go in this particular order, but I could pick any letter to choose from. So let's pick the spot that gets the M. Well, there are 11 spots to choose from. I've got one M, that gives us 11 choose 1 spots. Once I place that M, this leaves 10 spots for the other letters. Now let's pick the spots for the I's. There are 10 spots, and I've got to pick 4 of them to get the I's. So there's 10 choose 4 ways to do that. Once I do that, this leaves 6 spots. Now we'll do the same thing. Let's pick the spots for the S's. There are 6 spots available. I've got 4 S's, so I gotta pick the 4 spots that get them. That's 6 choose 4. This leaves 2 spots. And then we'll do the same thing, pick the spots that get the P's. Well, there's 2 spots left, and I've got 2 P's, so that's 2 choose 2. That accounts for all spots are now taken up. And now the total number of arrangements, I'm just going to use the multiplication counting principle. The total number of arrangements (11 choose 1 times 10 choose 4 times 6 choose 4 times 2 choose 2). So this is sort of how I always go about these problems, just by kind of multiplying these combinations, right? I think of it as some spots that I need to fill, and I'm just going to go down and fill them with the indistinguishable items. So I've got, like, for example, the 4 I's that we had, each of those I's, they're indistinguishable from each other. So I pick one group of indistinguishables, figure out which spots they get, and I use a combination to do that, and then at the end I have a multiplication counting principle. In Theorem 310, they give us another way to count, like as a formula, another way to count this. So there's some, let's see, the language they use here is let S contain n objects of k different types. So for our Mississippi, I have 11 letters of 4 different types. I have 4 different types of letters, the M, I, S, and P, and I've got 11 of them all together. And suppose I have N1 indistinguishable objects of type 1, N2 indistinguishable objects of type 2. So for example, like I have 4 I's, right? Like that's what they're getting at here, and 4 P's. Then the number of ways that we can arrange them is given by this formula with all these factorials in it. Now that'll give you always the same result that we just got, and in fact we could kind of see this work out up here. So I'm going to just use the combination formulas for each of these, and we'll see that we'll get the same expression we would get if we use the formula in 310. So I've got 11 factorial over 1 factorial, 10 factorial, times 10 factorial over 4 factorial, 6 factorial. I'm just using the combination formulas here. And then 6 factorial over 4 factorial, 2 factorial, times 2 factorial over 0 factorial, 2 factorial. Okay, now we're going to do some canceling. So this 10 factorial cancels with that one. This 6 factorial cancels here. This 2 factorial cancels there. I'm not going to multiply anything out. I'm just going to kind of simplify. What I have left upstairs is 11 factorial. On the bottom, what I'm left with is 1 factorial, 4 factorial, 4 factorial, 2 factorial. 0 factorial is just equal to 1. And so this is exactly what we would get. We have 1m, right? So there's my n1 factorial. We have 4 i's, so there's our n2 factorial, and so on, that we see in this formula. Let's do another example. So let's say we've got 12 books. We have 4 identical math books, 6 identical computer science books, and 2 identical chemistry books that we're going to place on the shelf. How many distinct ways can they be placed on the shelf? And so we're not saying that we want to group the like with like, right? Like we're not giving any restrictions on how we place them. But let's say if I did group those 4 math books together, then once I mix up those math books where they are, like that's the same, right? Like they're identical math books, so they're indistinguishable from each other. We have a total of 12 books, so that means n is equal to 12, or that we have 12 spots to fill. So let's pick the spots for the math. Then we'll pick the spots for computer science. And then we'll pick the spots for chemistry. So 12 spots to fill, 4 identical math books. I'm just going to pick the 4 spots that get those books. So that's 12, choose 4. Once I do that, once I place those 4 books on the shelf, there's 8 spots left. 8 spots left, from which I'm going to choose the 2 spots that get the computer science books. So that's 8, choose 6. Once I do that, there's 2 spots left, and 2 spots in which to pick the 2 spots that get the chemistry books. Always when you do it this way, at the end, this should just be like a K choose K, right? Like once I placed everything else, and you're giving the last sort of group, the last set of indistinguishable objects, there should be no choice left, right? Like those spots are just what they are, what's left. And so that last combination is always just going to equal 1. We'll use the multiplication counting principle. 12 choose 4, 8 choose 6, times 2 choose 2. And we could do this out with the combinations, or if you like, and you want to sort of see this simplify in terms of the factorials, like we did the last one. Right, we get the 8 factorials cancel, the 2 factorials cancel, 0 factorial is equal to 1. So I have 12 factorial over 4 factorial, 6 factorial, 2 factorial. I could either put it in my calculator this way or this way. Either way, let's see what we get. Let's see, I'll try with this formula. So again, I'm going to the math, and the probability menu, and option 4 is the factorial. I'm going to divide that by 4 factorial times 6 factorial times 2 factorial. 2 factorial is 2, so I'll just leave it there. And we have 13,860. This is the same thing that formula would give us, that what's it, 12 semicolon 462. If you're doing on a problem like this, I want to emphasize, you know, it's okay to kind of write it out as the combination and then just plug that into the calculator and get the same result. You don't have to go through all of this, or it's okay if you want to just use theorem 310 and go directly to this fraction here and plug that into the calculator. I'm just sort of showing the way that I think about setting up these problems is always starting with the combinations. It's just sort of how I think about, like, kind of assigning spots to these indistinguishable objects. All right, now we're going to generalize this binomial theorem so that it's not just for binomials, right? Binomial means very specifically 2 terms. So I could have more than 2 terms. In this case, I'm looking at the expression a plus b plus c. I've got a trinomial, and I'm raising all that to the 4th. And of course, I know that I'm multiplying. I've got 4 factors of a plus b plus c. So here I have them written out on the right side. And let's suppose we want to find the coefficient of a times b squared times c. When we multiply this out, right, if I were to think about distributing, you know, like all 4 of these across each other, basically what I do is I take from each factor, I figure out which of the 3 terms, right, is it this one, or this one? Am I going to pick an A from this one, and then a B from this one, and a B from this one, and a C from that one? Like, I'm just trying to figure out which of these do I pick each, or which term do I pick from each of these factors? And then I kind of go down the line, and as you expand out the whole thing, you've got all possible representations of how you could have chosen the terms that you pick from each factor, and then you add them all up. That's basically what distributing is when you multiply out something algebraically. So if I want to find the coefficient of a times b squared times c, what I really want to know is how many ways can I select 1a, 2 b's, and 1 c, where we are selecting a letter or a variable from each of the 4 factors. So the ways we can make this selection are, we're going to select 1a. So there's 4 factors. I'm going to pick which of these 4 factors. I'm going to select the A. That's 4, choose 1. That leaves 3 factors left. I'm going to select next the 2 B's. So there were 3 factors left. I'm going to choose the 2 factors from which I select the B's. And then I'll select 1C. And by then, there's only one factor left that I can choose. And now I'm going to use the multiplication counting principle. 4, choose 1, times 3, choose 2, times 1, choose 1. That's 4 times 3 times 1, or 12. That is the coefficient on a, b squared, c. So in the next theorem, theorem 311 down here, this just states it. We're looking at a specific question, but here's a generalized binomial theorem. So I'm not restricting it to binomials, any number of terms here that I'm raising to the nth power. And I get these coefficients, or I can help myself find these coefficients by using this. Now, it's not just a single combination. This is the formula from theorem 3.10. at bottom of the previous page, but it's the same thing we find, right, when I kind of go about it this way, right? I use the combinations there, but that's the same formula that we saw in that theorem. And then each of these, this sum is taken over all non-negative integers from n1 up to nm, such that the sum of those n's is equal to n. This is like saying, and we saw this in the binomial theorem, that the sum of the exponents, right, the sum of these exponents always has to add up to n for each term. So we're going to use this this theorem to kind of help us. We're not going to do a full expansion, but we're going to find the coefficient of a cubed b squared c cubed we're going to find the coefficient of that term in the expansion of 2a plus 3b plus c all to the 8th. So to get an a cubed b squared c cubed, that means that we want 3 of the 2a's. We want 2, right, because that's a b squared, we want 2 of the 3b's. And we want 3 of the c's. So 3 of the 2a's, the number of ways I can do that, I've got 8 factors, right? 8 factors here. So I'm going to pick, of those 8 factors, from which 3 am I going to pick the 2a? So that's 8 choose 3. And I'll multiply by that. I'm going to multiply that by, now of the 5 spots that are left, which 2 am I going to pick the 3b's from? So that's 5 choose 2. And then now there's 3 spots left, and that there's only one way, right? 3 choose 3. One way to pick the 3 c's that I'm going to grab. So 8 choose 3. 56, 5 choose 2, 10, 3 choose 3 is 1, so 560. Now I'm not done yet. That is not the coefficient I'm looking for, because notice there were coefficients on each of these terms. So I've got a coefficient 2, 3, and then 1, coefficient 1 on the c. So the term in this expansion is 560 times 2a cubed times 3b squared times c cubed. So 560 times, let's see, 2 cubed is 8, 3 squared is 9, and then we have a cubed b squared c cubed. And now I'm just going to multiply these guys. $40,320. And what we want is just the coefficient, so that's this value right here. Alright, moving on. We're going to talk about partitioning a set. So let's suppose we have 7 distinguishable marbles. So maybe all 7 marbles are different colors or have different patterns. And I want to place 3 marbles in one box, 2 in a second box, and 2 in a third box. So that accounts for all 7 marbles. We're basically partitioning the marbles in this fashion, and we want to know how many ways we can do this. So what we're doing in this problem, what we're thinking about doing in this problem, is partitioning a set of distinguishable objects. So let's do that right now. Let's pick the marbles for the first box. I've got 7 marbles. I'm going to pick 3 of them to go in that first box. That's 7, choose 3. Then I have 4 marbles left, so I'll pick the marbles that go in the second box. That's 4, choose 2. And then in the third box, there's 2 marbles left, and I want to pick the 2 that go in that third box, so that's 2, choose 2. And using the multiplication counting rule again, 7, choose 3, times 4, choose 2, times 2, choose 2. We already know this will be the same as that theorem, 3.10, 7 factorial over 3 factorial, 2 factorial, 2 factorial. And that gives us some value. Now, in this problem, we're thinking about, we have this distinguishable marbles, right? Each marble is different from the others. And in the last problems, we were thinking about arranging sets of indistinguishable items, that some of them are indistinguishable, like the Mississippi, right? Like not all the letters were different. But there's a connection here, right? Look at the way we went about it to partition these distinguishable objects is the same way we went about looking at arrangements where some of the objects were indistinguishable. And we're essentially doing the same thing. And the way in which we're doing the same thing is like saying, if I think about the Mississippi problem, whoops. Right, where we have 1 M, 4 I's, 4 S's, and 2 P's. Right? So, and there were 11 letters. And I said, well, think about these, that I have 11 spots to fill, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What we were doing in that problem was picking the spots, right, that, pick the 1 spot that gets the M, pick the 4 spots that get those I's, pick the 4 spots that get the S's. So we were thinking about, like assigning the spots to each of the letters. In that way, it's sort of similar to doing this stuff with the marbles, with these distinguishable marbles, because look, each of these spots is distinct, right? I have spot 1, I'll call this X1, X2, X3. These locations are all distinct, right? Because they're in fixed locations. So the way that the Mississippi problem is the same as the marble problem is that I am partitioning the 11 spaces. The 11 distinguishable spaces. Into 1, 2, 3, 4 boxes. Right, I've got box M, box I, box S, and box P. It's the same thing. So it's not just that there's a connection. We really are doing the same thing. We're just thinking about it in a different way. Now on the next page we have another theorem, but this is going to look pretty familiar. We're using slightly different notation, right? We have this C of, but now the rest of it is N, and then semicolon with all these N sub i's that follow. So this expression here, we're going to let that be the number of ways to partition a set S containing N elements into M sets, and each of those sets containing the N sub I elements. So it's like partitioning those 7 marbles into the 4 boxes, partitioning the 11 spaces, the 11 spots for letters, into the box M, I, S, and P. And that will always give you the same result as when you find that permutation of indistinguishable objects. So let's do one more problem to finish out this section. How many cards, or how many ways can 4 hands containing 5 cards each be dealt from a deck of 52 cards? So we're looking at 4 hands. And let's think about the way in which that this is a partitioning problem. I have 52 cards, right? And I want to partition the set of 52 cards into, in fact, 5 sets, not 4 sets. So we will partition the set of 52 cards into 5 sets. Those 5 sets are the 4 hands, and then the rest of the deck, right? The cards that don't end up in any hand. So let's pick the 5 cards that end up in the first hand. That's 52, choose 5. That leaves us with 47 cards. We'll pick the 5 cards for the next hand. 47, choose 5. That leaves us with 42 cards. Pick the 5 cards that end up in the third hand. That leaves us with 37 cards. Let's pick the 5 cards that end up in the fourth hand. And now there's 32 cards left, and 32, choose 32, or just now from there, one way to pick the cards that don't get dealt out. Theorem 3.12 says this will be the same thing as 52 factorial over 5 factorial, 5 factorial, 5 factorial, 5 factorial. There's our 4 hands, and then 32 factorial in the end. And whatever this is huge. Right, so we know that even just this one, right, we've computed this out before, that's about 2.5 million. And so then we're multiplying that by some other fairly big numbers. But this is the number of ways we can deal out 4 hands containing 5 cards each from a standard deck.